In the previous section, we studied a system of linear equations in two variables, and we used the substitution method and the elimination method to solve that system of equations. And we saw that geometrically what that is, if we have a system of linear equations in two variables, we have two lines and we can graph the line, and wherever they intersect is the solution. And so we saw how to find that solution, how to find that point algebraically by using the substitution or the elimination method. So now in this section, in section 5.2, we are learning how to solve a system of equations that has more than two variables. Now the substitution elimination method is still possible, but much more difficult, especially if you are larger than, you have more than three variables. So what we're going to do in this section is, instead of trying to stick with that substitution elimination method, we're going to introduce a matrix. Now, a matrix is just a rectangular array of numbers. All right, so we're making the observation that variables don't play a significant role in the solution of the systems of the linear equations, right? They just hold a position. And so these variables, we can remove them, and all we're left with are the coefficients of those variables. And that's what's referred to as a matrix, a rectangular array of numbers. And this can save a great amount of work, especially when more than two variables are involved. Now, we're going to start with a linear system with only two variables so that we can see how the process of solving a matrix works. Now, in this example, I have a system of linear equations just in two variables, x and y. And first of all, I want you to be comfortable with being able to write the system of equations in the form of a matrix. So for this matrix, all we're doing is we're taking the coefficients, this 3, the 1, and 1, and we're making that the first row. Now I have this vertical line here. This is an augmented matrix. The left-hand side of that vertical line are the coefficients of the variable. On the right side of that vertical line are the constants on the right-hand side of that equal sign. Then in the second row, we would use the -1 to 9. Okay, so now we can take this matrix, we've thrown away the variables, and we can solve this matrix by putting it in row-reduced form. Now, there are 4 requirements for a matrix to be considered to be in row-reduced form. And let's go over these 4 requirements. Number 1, each row consisting entirely of zeros lies below all rows having non-zero entries. Now, you may not always have a matrix that has a row of all zeros. Okay, that'll come up especially in the next section. But that is a requirement. If you have a row that has all zeros, it must be that last row. Number 2, the first non-zero entry in each row is 1. Now this is in reference to solving a system of equations, maybe substitution or elimination method, right? When you're trying to solve for x, right, you have to get x by itself. In other words, your coefficient of x must be 1. Right? So that first non-zero entry in each row being 1, that's in reference to the coefficient of the variable. Number 3, in any 2 successive non-zero rows, the leading one in the lower row must lie to the right of the leading one in the upper row. Right? These ones, again, the coefficients of your variable. So that's saying that the next row, that coefficient of the variable must be to the right of the coefficient of 1 in the previous row. That'll make more sense as we're going through the examples that we'll see momentarily. And then the 4th requirement is that if a column in the coefficient matrix contains a leading one, then the other entries in that column are zeros. So when we're solving for the x and the y, we don't want any of the other equations to have an x or a y. Right? When we use the elimination method, we eliminated one variable. So that we can solve for the other one. That's kind of what that's saying there. So we want everything else in that column to be zeros. So we're able to solve for the variables. Okay, so let's take a look at the method for writing this matrix in row-reduced form. This is what's referred to as the Gauss-Jordan method or the Gauss-Jordan elimination method. This can be used when we want to write the augmented matrix in row-reduced form. There are 2 steps, and we're going to repeat those steps for each column. Right? So when we're writing our matrix in row-reduced form, we work from left to right. We work in columns. We work from left to right, starting with the first column. Number 1, we want to set the leading 1, that's called our pivot, in the first column. And then step 2, every other entry in that first column, we want to set to be 0. And then once we have our 1 and our zeros in the first column, we'll repeat steps 1 and 2 for the remaining columns. So we would go over to column 2. We would set the leading 1 in the second column as the second entry. The second entry, we want to become a 1 in the second column. And then everything else becomes zeros. If we have a third column, then we would set the third entry in the third column to be 1. Everything else in that column, 0. Okay. All right, then the above steps can be accomplished using the following row operations. There's only 3 things that we are allowed to do with this matrix. Number 1, we can switch any 2 rows. Okay, now you would only want to switch the rows when you were trying to set the leading 1 in the first column. And if that first entry in the first column is not a 1, but you have a 1 in one of the other entries, you can switch rows. So that way, that's a quick operation that you can do to set your leading 1. Number 2, the other operation is to replace any row by a non-zero constant multiple of itself. Okay, in other words, you can multiply a row by any number that you want to. This second row operation is used when you're trying to set that leading 1. Right? If you cannot switch 2 rows and to give you a 1, the leading 1, then you can multiply that row by any number. And that any number is going to be the multiplicative inverse of that entry. Right? So if the entries would say to be 3, you would multiply that row by 1/3, because 1/3 times 3 is 1. Okay. And then in the third operation, you can replace any row by the sum of that row and a constant multiple of any other row. You're going to use this operation when you're trying to get all the other entries in the column to be 0. This is where you are adding an additive inverse to that entry, right? And you can't add, you cannot add constants to a row, but you can add another row to that row. So you would multiply the additive inverse of the to the row that has the 1, and then add that row to the row that you're trying to set to be 0. Okay, this will make more sense as we go through some examples here. So let's take a look. All right, so in this example, we just have this set up as a system of equations, 2 equations and 2 variables. So the first thing we would want to do is to be able to write this as an augmented matrix. So as an augmented matrix, we are throwing out the x and the y, and all we have remaining are the coefficients. So the first row is 2, 4, 8. Second row is 3, -2, and 4. All right, so we want to write this in row-reduced form so that we can solve for the x and the y. We have those 3 row operations, right? And we said that we are working in columns, starting from left to right. And the first thing we want to do is to get that leading term to be 1. Right, so we want this guy right there. We want that to become a 1. Okay, now we said in that first row operation you can switch any rows. What I mean by that is if this entry right here would have been a 1, you would switch those 2 rows to give you the 1 in that first position. But we don't have that in this case. So instead, we want to use that second row operation. We want to multiply the first row by a constant. We want to multiply the first row by the multiplicative inverse, right? The multiplicative inverse of 2, right? And you know what a multiplicative inverse is. It's the number that when you multiply it by 2 gives you 1, right? 2 times what is 1? And that's equivalent to dividing by that same number, right? So you could say, I'm going to divide everything in that first row by 2. In other words, we're going to multiply by 1/2. So I'm going to use this notation 1/2 times R1, where R1 is the first row. Okay, so when I multiply everything in row 1 by 1/2, essentially dividing by 2, right? 2 times 1/2 is 1, 4 times 1/2 is 2, and 8 times 1/2 is 4. The second row stays the same. Okay, now I have my 1. I've got that pivot. So everything else in that first column should be 0. So now I want this 3 to become 0. Okay, that's where that third row operation comes in. In order to force 3 to become a 0, I need to add its additive inverse to it, which is the same number, opposite sign. So I want to add a -3 to this number. We said that we cannot add constants to a row, but we can add a row to that row. So instead of just saying I'm going to add -3 to it, I'm going to add a -3 times the row that has the pivot, that has that 1. So I'm going to say row 2, is my row 2, plus a -3, that's the additive inverse, times row 1. Okay, now you may want to come over in the margin and do some work here to see what that's going to be. All right, so row 2 minus 3R1. Okay, I'm going to write that out. So row 2 is 3, -2, and 4. And -3 times row 1. Okay, I'm multiplying -3 times this first row. 1 times -3 is -3. 2 times -3 is -6. And 4 times -3 is -12. And now I'm going to combine my numbers here. I'm going to add my numbers. 3 plus a -3 is 0. That's what I'm wanting, right? I want to get a 0 there. -2 plus -6 is -8. 4 plus -12 is -8. So this is my new row 2. That's what I'm going to put here in my row 2. Notice that my row 1 stays the same. Right? I am multiplying that row 1 by a -3, but I'm adding that -3 times row 1 to the R2 and then replacing R2 with it. But I'm not actually changing anything in row 1 in the matrix. Okay, so look what we've got here. In the first column, I've got 1s and 0s. That's what I want. So once I finish that first column, then I can move to the second column. And so I start my steps over. I want the second entry in the second row to be 1. I can get that second entry to be 1 by multiplying by the multiplicative inverse or dividing by that number, right? I can say I'm going to divide everything in that second row by -8, which is equivalent to saying multiply by a -1/8. All right, so my first row does not change. So when I multiply 0 times -1/8, that's still 0. -8 times -1/8 is a +1, and that would be a +1 also, since it's also a -8. Okay, so I have my pivot in the second column. So now this should be my last step, to where I want this 2, right? I want everything else in the second column to be 0. So I want that 2 to become 0. And we said we can do that by multiplying the second row by the additive inverse of 2. So that's row 1. So the additive inverse of 2 is a -2. Okay, so in other words, what I'm doing is I'm taking my row 1, 1, 2, 4, and I'm adding a -2 times row 2, multiplying -2 times this row. 0 times -2, 1 times -2, and 1 times -2, and then add these. 1 plus 0 is 1. 2 plus -2 is 0, which is that's the reason why I'm doing this, is to make this entry become 0. And 4 plus -2 is 2. So I'm going to rewrite row 1 as 1, 0, 2. Now, this is in row reduced form. I don't have any rows of all zeros. I don't have to worry about that first requirement. But the first non-zero entry in each row is 1. All the other entries in the columns are zeros. Okay, so this is row reduced form. And so how do we interpret this? Right, we can convert this back to a system of equations. Right, the first entry in each row are the x's. Right, so I'm saying that this is 1x plus 0y. There are no y's, so x equals 2. And in the second row, 0x, there are no x's, plus 1y equals 1. So I have my solution written as an ordered pair as 2, 1. Now this is just a 2 by 2, only 2 variables. It would make more sense to use the substitution or elimination method instead of writing this as a matrix. But this is just to get the steps, right? Just to get an understanding of the steps. In the next example, we'll begin to see the larger system of equations involving 3 variables. And this is where using matrices can save us some time.